A very good afternoon to all the course participants of the 15th satellite-based training program on remote sensing GIS and GPS. This is module 3 on GIS. I am Vandita Shivastav and I shall be discussing with you today and tomorrow on spatial data analysis. So I would be covering some basic concepts on introductory concepts on spatial data analysis, and then we would discuss some functionalities and tools starting with today and ending tomorrow. So welcome you all once again to the session, and the agenda for my lectures is as follows. I would be covering introductory concepts such as why spatial analysis, what it is, and what is so special about spatial analysis, spatial and non-spatial queries, classification of the spatial functions, the general operations, and then we would discuss some specific operations which are classified into following function types: retrieval functions, selection functions, then measurement and classification functions, and overlay functions, and neighborhood and connectivity functions. So some of them I may discuss today and the rest I would discuss tomorrow. So let us begin with the introductory concepts on spatial data analysis. So the first agenda for the coverage is why spatial analysis, what is so special about spatial analysis, the two types of queries corresponding to the two types of data that we deal with in GIS, that is the spatial data and the non-spatial data, and then various types of spatial analysis and all I would also try to cover, but at the end of these two sessions, if time permits. So let's understand why spatial analysis. We already understand the term spatial analysis. That's pertaining to space, 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 right? So what all kind of things we could do with spatial analysis? One simple thing is whenever we are trying to study some phenomena that are geographic or spatial in nature, we can try to understand these phenomena or the processes. There are several examples of processes that might have already been talked about, such as soil erosion is a process that's occurring spatially in space, no, on Earth's surface. Then there are, landslides. All these are processes, earthquakes, even, and even expansion of a city, urbanization. These are all phenomena or problems or issues that are spatial in nature, which have got some spatial dimension. So anything, any process, any phenomena that is spatial in nature can be studied with GIS. And how we do it? We use spatial analysis tools. Then we can also reveal something that is not hidden, that is not identified, that is hidden in the database. Because the moment we prepare a geographic database in the form of MDB or GDB, like you might have already done in your practical sessions, uh, the database, even though it is complete and comprehensive, it still does not give us a view of what actually is there. For example, pattern of change of certain population, or it could be trend of how a particular phenomena changes. For example, urban expansion, how a city is growing in space and in time. These are all things that cannot be understood or revealed just by looking at the database. So we require some kind of processing in order to reveal this information or to identify new information from the database. So spatial analysis can do that. And finally, to carry out integrated modeling. So what is integrated modeling? We would understand in a minute. If you look at the slide, let's say this is the surface of Earth. So it could be any piece of land which is of interest to us, and we name it as our study area. Whenever we work in a project or study, we identify our study area, because any special problem would pertain to some place, some location. It could be a larger location, a larger area, or a smaller area, but we identify our study area. So let's say this is my study area, a piece of land on Earth's surface. Now, what I have done so far, what you might have done in your practical so far is, you might have prepared a geodatabase for this study area. So let's say you might have prepared some topographic features or some basic thematic layers. For example, the agriculture land, the land use land cover map. It could be a road map, river map. It could be administrative boundaries. So let's say you've identified all of this as a set of layers. Once you have done that and created your geodatabase, then comes the role of spatial analysis functions and tools. And how it plays a role? It creates a function, a new map as a function of input maps. So for example, new map is equal to function of some function of input maps, this map and that map. And then when you create this new map, it becomes part of this database to create another new map. So you can see there are so many, you can create so many new maps here. So compute this map plus that map for a new map. And then again store it back to the database, again create another new map. So it is like cyclic processing. That's what is written here. If you read this text, spatial modeling involves cyclic processing, retrieving one or more maps from the database. So it is retrieval, processing, creation, then again storing. So spatial and modeling involves cyclic processing, retrieving one or two maps or more maps from the database, which are used to create a new map. This new map then becomes part of the database and is available for subsequent processing. That's what we understand by integration and modeling. So we are integrating all this information together in GIS, and then we are processing it to model and to create new information. So that's what is integrated modeling. It could be just to describe a study area. It could be to prescribe some locations, some places, some possible places for a particular activity, or it could be to predict something in future, in future in space and in time. So accordingly, there could be different types of integrated modelings, and we would learn about a few examples on those. So that is what we understand by integrated modeling. I hope this is clear. Anything which is not clear to you, please keep writing your questions and I can clarify at the end in the interactive session. Next, we understand what is so special about spatial analysis. All of you might have already heard of these 4 W's and 1 H. That is the 4 W's are the questions that are spatial in nature, such as what, when, where, and why. These are 4 questions, and then how. So these 5 questions are the questions that are geographic in nature. So they can be answered for any problem that has a spatial relevance. We have already discussed what it means, and you might have already attended a few lectures on that. So I don't want to discuss more on that. So I would give you an example of some of them. So for example, this is a nature what? What kind of question? So what are most suitable locations of a dam? So basically, if you try to answer this question, you require information that is spatial in nature. Anything which is not of spatial relevance, such as books in a library, cannot be studied with GIS. You have to have a phenomena which is geographic or spatial in nature. It may not necessarily belong to Earth's surface, but it has to be in space and in time. It should be able to, described in space and time coordinates. So like location of a dam is something that is spatial, that exists at a particular location. So we are trying to we are trying to prescribe a model for prescribe a location for construction of a new dam, and therefore this this question is very spatial in nature. Therefore we can answer it with the help of GIS. You would have to break down your problem into smaller steps, but we can prescribe a location. Therefore such kind of modeling would be called as prescriptive modeling. Similarly, the next question, that is of type how will fire spread in next 2 days? This is a kind of question wherein we are trying to predict in future. So what exactly we are trying to say, that fire has ignited at a particular place, and now considering all the relevant parameters, variables, how this fire is going to spread in space and in time. Let's say in next 2 days, where all it will be spread. If you want to study this kind of question, to answer this question, the modeling type is predictive modeling, because you are predicting for future. And again, you can answer with the help of GIS because it's spatial in nature. So there are 2 things important for studying anything with GIS. One, that it should have, the phenomena should have spatial relevance. It should be, you should be able to describe it in the form of space and in time coordinates. Time is not necessarily required, but spatial coordinates x, y, or x, y, and z are required. The second important thing is anything you wish to integrate in GIS domain, you have to have a common spatial reference system, and there has to be some overlap, specifically if you are trying to perform some specific type of operations such as overlay operations. You cannot perform an overlay, for example, if you have two layers which are not having any kind of overlap, even if they have the same spatial reference system. So spatial reference is required because we are talking about problems of spatial relevance. So we require the georeferencing, what we call this type of georeferencing needs to be performed in order to further analyze your data in GIS domain. So let's move on to the next thing. This is the set of functions, types of functions into which the various functionalities of any GIS software are grouped, and these are retrieval, selection and measurement functions, classification or reclassification, overlay functions, and neighborhood and connectivity functions. So I would be discussing some of them, but before that I would like to discuss with you some general operations. Uh, and these are the very first step that you perform in analyzing your geodatabase is that you query, you question. Basically, it's simple English language query. Generally in softwares, you structure it in such a manner that the GIS software understands, the tool that is programmed to do this task understands your English. And that's why it's known as structured query language, SQL. So you can perform SQL queries, which could be of spatial nature or they could be of non-spatial nature. And then there are other things that you already know: arithmetic operations, relational operations, logical operations. This most of you might be already knowing, but I would show you the usage in GIS of these three types of operations before we discuss on specific functionalities. So let's study the first simplest thing in GIS, and that is querying your database. So you could actually query based upon the attribute information that's present in your layer, or based upon the spatial information. Accordingly, they are named as attribute query and spatial query. A real query could be a combination of attribute query and spatial query, or it could be two spatial queries and one attribute query, or several complex combinations of these. Or you could also generate new data sets from the original data sets based upon attribute querying, or based upon those functions, some selection functions, measurement functions, classification functions, etc. So scope of spatial analysis ranges from a simple query about the spatial phenomena to complicated combinations of attribute queries, spatial queries, and alterations of original data. In querying, we do not alter the data. We may create sometimes some new information, but that is again for visualization purposes. But we would see some operations which can alter your data. Okay? So we can generate new data sets from original data set by altering, by measurement, by selection, by retrieval. So all these functions I would discuss with you. But let's see some examples of attribute query and spatial query. So the first one is the attribute query. By the very definition, you can see that it would be the query that requires the processing of attribute data exclusive of spatial information. What does that mean? Let's say I have a parcel map. This is my parcel map which has got some information attached in the attribute table about the parcel number, parcel size, value of the parcel in terms of rupees or dollars or whatever, and the type of land use that it falls in. So for example, here we have commercial, residential, two types of land use. Now I ask a question to the database, to the GIS software on my database, asking please list all the parcel numbers and value where land use is commercial. It's a simple English statement. I have just tried to structure it with little bit, but it's a simple English statement. Now when you ask this query to the database, the answer would be 102 and 200,000, 104 and 250,000. To answer this query, I basically looked at the table because all the information about these parcels, even though these parcels are actually specially available here, but the information that I asked for is available in the attribute table. So only attribute table is required, only attribute information is required to answer this query. And that's why we call this query as an attribute query. So let's read it again. Requires processing of attribute data exclusive of special information. So it's as simple as that. But please note that this is only concept. How it is actually implemented in a GIS software could be different for different software. It may not necessarily be available in all software. It's basically dependent on how the software was programmed. For example, ArcGIS has got specifically the two types of queries, attribute query and special query, but not every other GIS software would have it. So you have to find out, once you understand these concepts, you can find out how to ask such a query, how to formulate this in a particular GIS software. So let's understand now the special query. It involves selecting features based upon location or spatial relationships, which require processing of spatial information. Which means now the special query, answering a special query requires processing of spatial information. It may or may not include attribute information, but it has to have processing of spatial information, which means you cannot answer this query without using the spatial information present in a layer. So here is an example. Please list all the parcels within a specified distance, let's say within 10-meter distance or within 5-meter distance, depending upon the scale of the map. And to know that, I need to tell my location. I'm standing here, and now please show me all the parcels that are within 5-meter distance from me, or from where I'm standing. So notice that the question itself has got some special component. And even to answer this question, you need to access this location of where I am present, that is the XY coordinates. Then only you would be, creating a sort of virtual buffer of 10 meters around this, and then identify which are the parcels that are within 10 meters of distance or any X distance. So answering this query requires processing of spatial information. That's why it is a special query. Now a real world query could be a complex combination of these, as I already told you. Maybe we'll have a few examples on those. But before that, let's now understand the usage of these three kinds of operations in GIS. So if you already know what are arithmetic operators, then goniometric operators are there, the trigonometric operations which involve angle calculations. So sine, cos, all these kind of operations, not just arithmetic, but all these operations can be used in GIS. And here is an example. This is an example of raster wherein you do pixel by pixel calculations. It could be pixel by pixel, it could be based upon window or anything. I'll discuss that in tomorrow's session. But if you look at this simple statement, raster 2, this is a sign of assignment. So raster 2 is assigned as equal to raster 1 multiplied by 5. So simple multiplication we are using here on a grid. So this is a grid of, let's say, n by n size, and we are multiplying it by a value 5. So each of the pixels in this raster 1 would be multiplied by a value 5, and that will result in raster 2. You can imagine raster 1 as a digital elevation model, for example. So multiplying by a value 5, what will it do? The significance is that this would exaggerate the values by a number 5. So any difference which is minute will also be exaggerated. So you would be able to see it more clearly. So operations are simple, but how you use them in GIS is what is your innovation. So you can use all these operations innovatively, and you could fulfill some of the requirements for a particular analysis. So this is one of the examples. I'll show you some more examples on this. In fact, using some similar thing only, the very popular NDVI index was designed, and it is one of the most popular indices or ratio based indices in remote sensing, just using the simple arithmetic operations. But it took it 10 years to design that. Anyway, that is image processing part, but here we are talking about the raster GIS, and I hope you already understand what is the difference between a raster map and an image. So next, let's talk about the relational or the comparison operations. They are all available here on your keyboard. You might have seen all these signs. Different software would use different nomenclature for telling these signs. For example, some would use this hash sign for not equal to. Some may use less than and greater than to denote the not equal to sign. How it is read, let's see it here. This is a relational statement. This blue color statement is a relational statement. And how it is read? C is assigned as equal to A not equal to B. This statement is true when A is different from B. If A is same as B, then C will get a value 0. If A is different from B, then C will get a value 1. So what does it signify? If you see carefully, it's basically making out the differences. So wherever you have a difference, C will be 1. Wherever there is no difference between the values of A and B, it is 0. Now if you imagine your A and B are land use land cover maps of your city for 2 different years, let's say 2010 and 2015. So whatever changes have occurred in these 5 years would be marked as 1 as true in the areas, especially in the map C, while the ones that are unchanged will be marked as 0. So you can actually do some quick change detection using this simple statement, which is C is assigned as A not equal to B. So you see, you can use it really innovatively to do very interesting analysis. So relational operations, arithmetic operations, and logical operations that I'm going to discuss next can be used very interestingly, and they are required in almost every step in your analysis. Another example of such a relational statement is very simple statement wherein you can perform comparisons, and that's why they are known as comparison operators also. Field is less than field and then relational operation and then value. An example is area less than 400,000. So what basically you are trying to do here, you want to see, because the moment you say area means you are talking about polygon features. So you basically want to identify all those polygons whose area is less than 400,000 units. When you perform this, it looks something like this. In the attribute table, you would get all the records that satisfy this condition as selected. So here the red color shows the selection. Correspondingly, in the map, you would see that all the polygons that satisfy this condition are highlighted here in red color. So you notice here that these polygons are smaller in size. There is a bigger polygon here, but that's not selected because you have put a less than condition. So you understand that these are all the polygons that are having area less than some value. So you can also convince yourself and you can check whether what you performed is really something that you desired. So you can put a cross check whenever you perform such queries by a simple common sense. So that was some examples of relational operations. Now I would discuss with you on the logical operations. And these operations are very popular. They basically come from logic theory, and it's very widely used in operations management. It's a field of operations research, but it has been applied in many areas, including electrical engineering, in electronics, in even in medical, bioinformatics, at all the places, including GIS. So here I'm going to discuss only the GIS usage of these logical operations. I just wish to tell you that those who know it, they may ignore, but those who are exposed to it for the first time, I wish to tell that these three operations are the basic three operations, and or not. Please forget for a moment your English and. This is slightly different, and or not, but it's very simple. You would understand in a minute. An XOR is a derivative, which means it can be derived from the basic operations, which are these three. So we can derive XOR. You would see that. So let's see what they mean and how we can use them. The logical conditions are specified. So you basically require three things. You basically have three things in when you perform logical operations. The first thing is the operands, the data elements. For example, your map A, map B, or condition A, condition B could be treated as your, they could be used as operands in a logical operator. The second is the operator, whether it is AND or NOT or XOR or any other operator. So that basically establishes a relationship among the data elements. And third thing is the output. The cell values of the output raster is either true or false. So anytime you perform logical operations, please note that the outcome will always be true or false. It is also possible to have fuzzy version of these, then they may have some values intermediate, but in most of the GIS software and at most of the times you perform the Boolean operations. So it will be true or false. Now here is an explanation of what they mean, and I have put their set theory equivalents to make it simple for you to understand. If you recall the set theory that we studied long back in our schooling, uh, this is the universe of discourse, and when you want to express and, it is equivalent to intersection. And what it means, when both the conditions A and B are true, only then the output of AND will be true. So A and B will be true only when both A and B are true. Otherwise, if any of the conditions stands false, the output will be false in case of AND operation. The OR operation is, on the contrary, would be true if any of the conditions is true. So you see the whole A and B areas are filled here. Then now discuss the not. A not B. A should be true but not B. So the result is this portion. This portion is excluded, this is also excluded. Similarly, B not A will be this part of B where A is not true, and since this is an overlapping area, so you will result in only this. And the last one is the XOR, which is A XOR B. That is, A or B could be true but not both at the same time. Therefore, the common condition has been taken out. I told you that this is a derivative. You can also look at it here. You can derive XOR from either AND and or by combining two NOTs. So for example, you can derive XOR using either AND and OR. If you minus AND result from the OR result, you will get XOR result, because this area, this common portion, is not included in the XOR. Similarly, if you combine A not B and B not A, you will get XOR. That's why XOR is a derivative. In fact, there are many more other operations that are available, but generally whenever a GIS, a raster calculator or any calculator is designed, they put only these four operations because they are most common, and you can create any derivative operator from these three. So otherwise there are XNOR, then NOR, then NAND. There are many others. You can combine, keep on combining and getting the derivative operators. We would see their usage, how we use them in GIS in a minute. Or maybe, I think I have not included that here, but in the retrieval and selection, we would have a lot of examples of AND or NOT XOR. So now let's discuss some of the spatial function analysis and tools. Till 5 o'clock, I am given the time of 5 o'clock. So let's discuss the retrieval functions now. I already discussed with you that these are the four types of functions in which we can classify. The retrieval and selection functions are simple functions wherein we just perform certain queries to select or to retrieve some information. The measurement and the classification functions are the ones wherein we may create some more, but we do not manipulate the topology or the features of a particular layer or particular features. The third type of operations are overlay operations where we, put more than two layers together, more than one, that is two or more layers together, and we may modify the topology of the original layers. So there is a manipulation taking place there. And these three categories of operations are the ones which talk mainly about the location at hand. But the moment you talk about surrounding locations, because you are also interested in your neighborhood, what exists in your neighborhood. So there comes the fourth type of class, the functions, that is neighborhood functions and connectivity functions, which take into account your surroundings. So that's why it is classified most popularly in this classification scheme. So now let's discuss on the retrieval and selection functions. It can be done using different operations in different ways. So we would learn a few ways of retrieving our data. Pixel information is a very common tool, specifically in the raster analysis softwares such as Ilves, wherein you can see even the spatial analyst of ArcGIS also would have this pixel information. So we can retrieve a lot of information of a particular location using the pixel information window. Then we can do interactive spatial selection. We can do selection by attributes, selection by spatial relationships. So we would see examples of each of these in a few minutes. Data retrieval and selection. So what exactly it means? It involves selective search, manipulation and output of the data without requirement to modify the geographic location of the features involved. Spatial and attribute data are retrieved when you perform retrieval and selection. No changes are made to the location of spatial elements. This is important. No new spatial elements are created. Examples of retrieval would be what exists at a particular location. Retrieval of spatial data, where exactly is forest type, where is a steep slope in my study area. So these are all the type of examples of retrieval operations. Retrieval of using retrieval of information can be done using logical conditional arithmetic operations also, or it can be done using spatial relationships. So I would show you, here is an example of pixel information window. So for example, this is your study area and you drag all the information, all the maps to your map window. So you include the soil map, the rock map, the slope map to your map window, and correspondingly all the information would come here, the attribute information would come here in the pixel information window. Now you move your cursor within the map window and let's say you click at a particular place and you want to know what are the attributes, what is slope for example for this particular pixel. So all the things would be listed here. So this can quickly retrieve your data. Similarly, you can also perform it in this manner. That is, you do not drag anything to the map window, but you drag all the other layers to your pixel information window. Please note that all the layers should be having the common reference system. The geospatial reference system should be the same for all of these, the projection, the coordinates, etc. They have to have some overlap within this map window, right? So when you move your cursor, for example, here is the cursor. Now all this information, geology, rainfall, DEM, the digital elevation value, the land use, the geology, lithology, everything is listed here. So you see, you just move your map once you have digitized your layers, once you have prepared a geodatabase, an accurate geodatabase, then the retrieval becomes so quick and so easy. So you can know about anything and everything about your study area that about which you have collected the information. So it becomes very easy to analyze and to understand about your study area. Another example is retrieval of information using attribute values. This is known as attribute mapping and this is an example from Ilves. You have, let's say, the city block map, and it has got the identifier domain, that is each city block is represented as, is given one ID identifier, and then there is an attribute associated to each city block, that is the land use. So now you can use this attribute to display this map, and that's what has been done here. This is the outcome of attribute mapping, and if you compare this map and this map, this gives so much information about the land use distribution. Here you just see the IDs and you really can't get more a lot of information from this. But this immediately tells the pattern of distribution of the land use type. And you can see that the residential is towards the center, and on the sides are the commercial and the industrial, and then there are some recreational here. So you immediately get a picture. So you see, you can retrieve data, you can this information was already present in the table, but the moment you show it as a map, this information is revealed. So that's what I mentioned in the beginning, that you can reveal or you can identify the unidentified information that was present in the database. So these are a few examples of retrieval. Now we discuss about the selection, and then we stop for queries. So special selection can be done with the help of logical operations and with the help of topological relationships. So the logical operations we already discussed, but I would show you some examples, and then we would discuss about topological relationships. So if you see here, this is simple interactive selection. That is, you click on a record, the corresponding polygon is selected. Or the vice versa, you drag in a circle or a window and all the connected polygons are displayed here, and correspondingly they are also selected in the attribute table. So they are highlighted in red color. This is simple interactive selection. You have not performed any queries here. Other type is that you formulate a condition. Okay, I would show you an example here. Yeah, we have already understood the logical operations. So here is a simple query which we already saw. Here is a combination, area less than 400,000 and land use equal to 80, which means both of these conditions have to be satisfied to make the end true. In case of or, either of these conditions need to be satisfied. Not, it should not be land use 80, which means it could be any other land use but not 80 land use. 80 could be just a number given assigned to a particular land use type. So let's see an example here for this combined query. So here we have combined the attribute conditions. Now you see, we had already seen the result of this, and there were more polygons if you remember. But in this case, when you combine the land use equal to 80 condition using the AND operator, the number of records selected reduces. Why? Because here it has to satisfy not only this area condition but also the land use 80 condition, and that's why the number of records reduces. And you see again that the polygons that are selected have got a smaller area. So that's how you can perform, you can combine the attribute conditions and you can perform selection. Then you can also perform selection using the relationship that exists between these features, the point, line and area features. So here I have given example of polygon features because with polygons we can have maximum number of spatial relationships. This is an example of a disjoint relationship. Whenever the two features do not join to each other, this is known as disjoint relationship. In this case, they meet because they are touching the boundaries. In this case, both polygon feature A and B are equal, exactly equal. So this is an equal relationship. Especially they are equal. Their attributes may be different, but especially they are equal. In this case, there is an overlap that exists between the two. They are neither equal nor completely disjoint. They are overlapping in between the equal and the disjoint, or in between the equal and the meet. This is B covered by A or A covers B. In this case, B covers A. B is bigger, A is smaller. B is the black boundary polygon, A is the red boundary polygon. In this case, B is inside A because B is smaller, A is bigger. And this is completely inside. Here, in this case, it is touching the boundary. So covers and covered by, in these two cases, there is a touch of boundary from inside. But in these two cases, there is no touching of boundary between the two features. In this case, B contains A. So you can see that both inside and contains are the same thing. But in this case, A is bigger, B is smaller. So B is inside A. Or we can say A contains B. So the condition is basically the same. The relationship reverses. Right? So we can't exchange, we can't mutually exchange A with B. In these cases, we can mutually exchange A and B. We can say A is disjoint from B, B is disjoint from A. A meets B, B meets A. A is equal to B, B is equal to A. A overlaps B, B overlaps A. But we cannot say A is covered by B, B is covered by A. You see, we can't mutually exchange these two. So they are not mutually exchangeable operations. That's why I put them explicitly for you to understand. We can use these in our spatial selection. For example, here let's say we have three informations. The cities are represented here using these cyan color points. The wards are the the black boundary polygons, and the highways are the red color or the magenta color lines which are crossing by the states. Now we say that we want to select all the cities that are in a particular ward. Now this ward is number 241 and this is this ward. So how we go about it? We first make an attribute query saying please select ward number 241. Once we select this, now we use a spatial relationship inside. We use this relationship to find out which are the cities that are inside this particular ward. So this is a point in polygon type of query, and it results in all the cities that we ask for. So all the cities that are within ward number 241. So this was a usage of inside query. Similarly, here is an example of inside once again. All the cities that are within the state of Georgia are selected. This is a similar query. Let's see some more. Select the highways that run partly through the state of Georgia. Now, you would wonder how do I select these highways, because highways are not something that are contained in a state. They run partly. So inside would not work. Meet would also not work because they are crossing by and some may not meet each other. So overlap is the only operation, is the only spatial relationship that would result in selection of all those highways that are crossing by this particular state. And therefore you need to perform one attribute query to select the state of Georgia and then one spatial query using the overlap spatial relationship to find out all the highways that run partly through Georgia. Similarly, you can find out all the neighbors of the state of Georgia using the meet condition, you see, and maybe a few more. Yeah, this is the ninth type of relationship that we did not discuss there, but this is simple and known to all. This is the relationship of distance. Show me all the cities that are within the distance of 100 miles from Atlanta. So a virtual buffer is calculated and all the cities that fall inside that virtual buffer are retrieved here. So all the cities that are within 100 miles of a particular feature, in this case the city of Atlanta, are resulted. So that's how you can select with the help of buffer using the distance relationship. Now here is an assignment for you. Maybe you would have some practical data available with you. You would have a road layer and you would also have some building layer. Just imagine that two of the buildings are your hospitals and three or four roads are the major roads. So you can even create a column in your attribute table, and then you please try to identify all the major roads that are located within a distance of 200 meters from a hospital. Please try to perform this query. So we stop here, and I would like to know how many of you did this query in practical class in your, on your software. And then maybe I can show you the example and the answer, how you approached to this and how you, whether you got the result or not. So I break here, I stop here.